Okay, we've got some specially named processes. I think I said before that we use them because they're easier to model. We've done the case, if we look at the first law, we've done the case where work is equal to 0. So work equals to 0 on a PV diagram looks like we go from here to here, either down or we go up. This is the work equals 0. So this is our isovolumetric, iso meaning same, or isochoric, where choric stands for volume. So this is a constant volume process where the work is equal to 0. We've also looked at the case where the change in internal energy is equal to 0. That's an isothermal process. So this is PV, and this is like this. This is a constant temperature line because pressure going as 1 over volume, basically. This is a constant temperature. So a process like this from initial to final, here's initial to final, has a change in internal energy equal to 0. And so this is isothermal, same temperature. And so it makes some sense that we would have the case where we would have Q is equal to 0. So Q equals 0 is called adiabatic. And we need to say something about even just doing these kinds of drawings before we draw what's happening here. There's something implied when we can do a drawing like this, because what this means is that we have what's called a quasi-static process. What does quasi-static mean? It just means it's a very slow process, and the idea is that if we start at our initial point, we get to the next subsequent points by staying in thermal equilibrium every time along the way. And so that means we can connect these dots, because if we're not in thermal equilibrium, we don't know where we are in a PV diagram, because we don't actually know the temperature. The temperature could be fluctuating for our system, and we can't actually draw it nicely on our graph. And usually that's not a problem. We can do it slow enough for these types of situations, for everything to stay, for us to stay at a constant volume, for us to stay at a constant temperature, if we make sure things are set up where we're in nice contact with a heat bath or something like that. But for an adiabatic process, often these are fast. Often in the real world, these are fast processes where we don't have no time for heat exchange, for the heat to go in or out. And that's not a quasi-static process, but we can imagine this process even to be a fairly slow process. And so the setup is sort of like you set up your piston just as normal, right? So here's a piston, and we put it in an insulated box here, okay? Maybe with the lid on, I don't know. So it's really well insulated. So this is insulation. All right, so this is insulated. So there's no way to have heat exchange with anything. And then we slowly, for example, drop some weights on here so we can compress this, okay? And so what's going to happen is this is insulated. We're going to compress. So we're going to do work on the system. This is work less than 0. We're going to increase the pressure, and at the same time we're going to change the temperature. All of those things are going to happen so that Q is equal to 0. And the book goes through the derivation. I'm not going to go through it, but basically what happens is for an adiabatic process, you can prove using the first law and our relationships between PV equals nRT and change in internal energy equals this. You can show that what stays true is the pressure times the volume raised to gamma. Gamma is, just to remind you from last time, gamma is Cp the heat capacity at constant pressure over the heat capacity at constant volume. For monatomic, that would be 5/3, is equal to some constant. What that constant is depends on where you are on the PV diagram. So for a monatomic gas, gamma is equal to 5/3, right? 1 2/3, so about 1.67. And so what this looks like is on a similar diagram over here. If we start here and we do an adiabatic process, then we get P V to the gamma equals some constant, right? So if I plot that, that would be P is proportional to 1 over V to say 1.67. This plot right here is a plot of pressure is proportional to 1 over V because it's coming right out of this expression. And so, in fact, the adiabatic process would look something like this, slightly steeper if we wanted to go. Now, it's not going to go to the same final pressure, but if we want, or the same final temperature, but if we were going to go to the same final volume, that would be an adiabatic process. So this is isothermal, constant temperature. And then this is an example of, just a little steeper, this would be an adiabatic. Now, even though this is true, it's also the case that PV equals nRT is still true. So you can rewrite this if you don't want it in terms of pressure and volume. You could say pressure times volume of gamma minus 1 is equal to a constant, right? That's still true because this is V to the first power. So those two together give me V to the gamma, and gamma is greater than 1. So for monatomic, this would be just a 2/3 at this point. And then you can substitute in nRT. And so you can, just by substituting that in, you can get then T times V to the gamma minus 1 is equal to a different constant, another constant. And what that means is just along this path that we take, if we can draw it, that the heat exchange is equal to 0, but we definitely have a change in internal energy, and we definitely have work that's being done. And the change in internal energy just comes from knowing my T initial and my T final. My T final is going to be lower in this case. And then I can find the work that's done, which would, of course, be the area under the curve for the adiabatic. And that work is equal to, for an adiabatic process, since Q is equal to 0, we can see, of course, that the work done, work for an adiabatic, is just equal to minus the change in internal energy. And so this makes sense. This is positive work done because this is the direction that we're going. But we've got the final temperature down here, this new final temperature from this initial. This blue is all the same temperature. This is a lower temperature, and so my internal energy change is negative. So a negative of a negative gives me a positive work that gets done. So it's all consistent with the diagram. So an adiabatic process is one where pressure times volume to the gamma on this curve is equal to a constant. It's going to be different for different curves, for different starting places. But it's also the case that the ideal gas law, because this is assumed to be an ideal gas, still holds true. So you could also rewrite it as T V to the gamma minus 1, or you could write it as a relationship between pressure and temperature if you like. Any of those things will work.